We will now take a look at Chapter 10, which is all about exponential and logarithmic functions. Before we start applying calculus tools to them, though, let's do a quick review of what those functions really are. So this video is the pre-calculus, sort of just-in-time support for exponential and logarithmic functions. If you need more practice with them, please take a look at pre-calculus review package, where you'll find more examples and exercises and explanations about what exponential and logarithmic functions are. So exponential functions are of the form y equals a to power x, where a is some positive number, okay? So for example, for our first graph here, let's take a look at the functions 2 to power x and 2 to power minus x. Recalling exponential laws, which I hope that you can, again, either remember or look up so you're more familiar with them. Remember that negative powers are actually positive powers, but on the bottom. So 2 to power minus x is actually 1 over 2 to power x, which alternatively can also be written as 1/2 to power x. Now, if we would like to sketch these, and if you don't remember the shape, the first thing to do is to construct a table of values. So I'm going to construct both of these graphs within the same table of values. So I'm going to have x, 2 to power x, and then 2 to power minus x. Now, whenever you construct a table of values, the one thing to remember is that you do want to pick a variety of numbers, so don't discriminate against negative numbers. You also want to know what the graph looks like on the negative side. So let's plug in, say, 0, 1, 2, -1, -2, and then hopefully that should be enough for us to see the shape, and if it's not, we'll plug in more numbers. So 0, if I plug in 0 up into the power, 2 to power 0 is just 1. 2 to power 1 is 2. 2 to power 2 is 4. 2 to power -1 is 1 over 2 to power 1, so 1/2. 2 to power minus 2 is 1/4. Okay, and then when I'm plugging in for the 2 to the -1, feel free to pause the video here and actually try the numbers for yourself. You will notice that if I plug in 0, I will also get a 1. In fact, anything to power 0 is 1. 2 to power -1 is 1/2. To power -2 is 1/4. But then here, something interesting happens. If I plug in -1 into the minus x here, I'm going to get 2 to power -1. So 2 to power 1, or just 2. And similarly for the next one is 4. So we see that these graphs actually flip the values around. Let's now try to actually sketch them. So we're going to go through the points for the first graph of 2 to the x and sketch those on the graph. So at 0 I have 1, at 1 I have 2, at 2 I have 4. And on the negative side, I get -1/2 and then -1/4. And I know that this trend will continue. The higher the power, the higher the graph will grow. The smaller the power into the negative, the smaller of a fraction I'm going to get. But it is important to notice that I'm never going to be able to get a negative number, right? No matter how big a negative number I plug in here, it's going to get smaller and smaller in fraction, but never turn negative. So this is 2 to power x. If I'm sketching 2 to power -x, I will note that it's the exact same graph, but flipped in the y-axis. So it's going to be the graph that is actually decreasing this whole time. Now, one thing to note here is anything to power 0 is going to be 1, which means that no matter what exponential function I have, I will have the y-intercept at 1. Great news. We now know what an exponential graph looks like for positive and negative powers. This is just for one value of the base number, though, which is what a is called. Let's take a look at how that compares between different bases. So here I have 3 to power x, 5 to power x, 4 to power minus x, and -4 to power x. Notice with this last number that it's actually 4 to power x, then all negated. So it's not -4 to power x, because for the definition of the exponential function, the base has to be positive. So this is actually just a negation of an exponential function. Take a minute here and actually sketch these graphs using the table of values to see how they work on the same graph together. How does the base affect the shape of the graph? This is what you should get. So you notice that the graph with 3 to the x will rise slower than the graph of 5 to the x. So for example, if I now try to sketch 4 to the x, it will be somewhere in between them. The negative powers will be the graphs that are the same but in the decreasing manner. And if the whole function is negated, then it's going to be flipped around the x-axis. A couple of general trends are becoming pretty obvious about the exponential functions. Specifically, if I take a limit of an exponential function as x goes to infinity, a number raised to a really large power is a really large number, so this will be infinity, which means that generally the exponential functions grow when a is bigger than 1. If I have a fraction, that means that I really have a negative power like I did here, which means that the shape of the graph will be decreasing. So the limit as x goes to infinity of a of x is equal to 0, approaching the x-axis for the values of a less than 1. Remember that for our exponential functions, a have to be positive. So in both of these cases, a's are actually bigger than 0. The other thing to mention about exponential functions in general is that the reason these are so useful is because they model processes that multiply or divide by the same amount within the same time frame. So for example, this graph of 3 to the x will model something that gets tripled every fixed time interval. Let's say every week, if my x-axis is in weeks, the number of, let's say, bacteria gets tripled. The functions that are exponential but decreasing will model processes such as decaying, which is the case with things like radioactive materials, where we hear words like half-life, which means that every fixed amount of time, the amount of material gets halved, divided by 2. They will also model things like how the drugs get absorbed and processed by the body. We will see a number of different applications of exponential functions throughout this entire chapter. Let's next take a look at something a little more calculus inspired, and that is let us attempt to find a tangent line to the actual exponential function at a particular point, at 0. It is going to be at the y-intercept, so we will be looking for tangent lines right at this point right here. Let's see if we can come up with a general equation to describe them. So, as always, we will start with y minus y naught equals mx minus x naught, where m is our slope. So the point here is x equals 0, which means that y equals 0 is a to power 0, which is, of course, equal to 1. And this m is the slope. Now, I don't yet know how to take the derivatives of exponential functions, so I will leave the slope value as just m. What do I have otherwise? I'm going to have y minus 1 is equal to mx minus 0, or if I expand it out, I'm going to have y equals mx plus 1. Well, this is a very nice equation where all I have no idea how to describe yet is the actual slope. What we can do is try to eyeball it from the graph and see if we can see something interesting. So let's take a quick look at what these functions look like. So here I have, let's say, y equals 2 to the x, and I have a line with equation y equals mx plus 1. M is supposed to be the slope of this function at 0. So I'm simply going to slide the slope around until I can be fairly certain that I have approximated the slope to be something. So I would say that this looks like a pretty good approximation of the tangent line at 1. And so my slope there is approximately 0.69. Okay, what if I wanted to take a look now at 3 to power x? Well, I know from what we've just sketched that that graph will rise quicker, which means, so let me take away the 2, which means that the tangent line for 2 to the x is no longer the tangent line to this graph. So if I try to eyeball what this tangent line look like here now, I would say it's something like this, right? This looks pretty tangent at 0. So the value here that I have is 1.13. Now this is a complete approximation. I'm not after any kind of rigorous definition. But what is interesting though is that for when I looked at the graph at 2 to the x, my slope was just below 1. When I looked at the graph of 3 to the x, my slope was just above 1. So now I wonder, what should the base be for the slope of my line to be exactly 1? So what is this line with the slope of 1 actually going to be tangent to? There must be an exponential curve that this is tangent to at 0. And that is indeed the case, and that curve is e to power x. So the base number for which the tangent line has slope 1, the perfect diagonal line here, is that constant e, the natural exponent. So I've just summarized all of our findings on this slide here. For 2 to power x, the slope was less than 1. For 3 to power x, the slope was bigger than 1, which means that for some number between 2 and 3, the slope is 1. And that number is what we call e. In fact, it's such a nice number, I'm going to put an exclamation mark here. That's what e is. E is a number for which the slope of the tangent line at 0 is equal to 1. Now, e itself, if you plug it into the calculator, you'll notice that it can be approximated. It's never ending, it's transcendental, which means that there is no end to its decimal expansion, but you can approximate it with something. It's approximately 2.7. A lot of problems, particularly in this course, because of their applications to biology and other life sciences, will use e as a base, as opposed to some actual number, like to some whole number, like 2 or 3. This base will become extremely useful in most of the things that we're going to see. And in fact, we will generally use both exponentials and their inverse functions with this base. Now, speaking of inverse functions, let's take a look at what that actually means. Once again, this is going to be a quick introduction to what inverse functions actually are. For more detailed explanation of what they are as an abstract concept, please take a look at the precalculus review package. But the idea behind exponential functions is this. Let's say I have x, my input. If I apply function f to it, I get some output f of x. If I would like to reverse the process and go back, I'm going to apply what we call an inverse function, and we have the notation for it, f of f to the power minus 1. Now, the notation is not the best, so please be careful. F to power minus 1 of x is the notation for the inverse of the function f, not the reciprocal. So this is not the actual power. So this is not 1 over f of x, okay? The notation is not the best, but it is a good shorthand. We will talk about inverse a lot more than we will talk about the reciprocal, so it makes sense to use that as a shorthand, okay? In the most reasonable way, the word inverse is exactly what it means in English as well. So for example, for just a really quick intuitive example, if my function is, let's say, 5x, so my function multiplies everything by 5, then its inverse is going to do the exact opposite or revert the process, which means to divide by 5. So in this case, the inverse function will just be x divided by 5, okay? If my function was to add a 3, then the inverse would be to subtract a 3. So verbally, the inverse function simply undoes what the original one did. Symbolically, we write that as if I apply my function to x first, and then I apply the inverse, then I'm simply going to get my x back. Whatever f did, f inverse undid, and I was able to get my original value of x back. Now, it doesn't matter what order you actually apply inverses, the functions in. So if I apply the inverse first and then the function, I should also get my x back. Both are functions, both can be applied in any order. Analytically, we say that we actually reverse the roles of x and y. And if you were to solve for it, or if you remember from precalculus how you would solve for it, this is how you would find an inverse. You reverse the roles of x and y in your formula, and then you solve for y to get, once again, an explicit function of x. Graphically, reversing the roles of x and y means flipping the graph along the y equals x line. So we do this a lot. Again, in precalculus, you've probably seen that. And we will come back to this once we talk about the graphs of the inverses of the exponential functions. The one thing that does mean for the function, though, is that for a function, in order to have an inverse, it must also pass the horizontal line test, the test for actually having an inverse. Thinking about inverse functions in terms of exponential functions, the inverse of an exponential function is what we call a logarithmic function. So the exponential function itself, the way to calculate this, the process is fairly straightforward. 2 to the power x means that we raise 2 to power x. The opposite process will ask what power did we have to raise to get the outcome. So in the logarithmic function, we're after the power. So if you're trying to compute logarithm, first of all, you have to look at the base. Here it's 2, and then the inside. And in order to actually figure out what the number is, this will correspond to the power to which you had to raise this base 2 to get this number x. Now, just to get a little bit familiar with the calculations, let's do a couple of examples. So, for example, logarithm base 2 of 8 means I am trying to figure out what is the power to which I have to raise 2 to get 8. So 2 to what power is equal to 8? Well, these are nice numbers, and I can see that that number is going to be 3. So this logarithm value is 3. 3 is the power to which I have to raise 2 to get 8. Okay, let's take a look at the next one. To which power did I have to raise 3 to get a 1? So maybe on the side here, 3 to which power is equal to 1? Well, anything to power 0 is 1, so this logarithm is going to be 0. Next one, 3 to which power will result in 0? Well, we've discussed that on the very first slide in this video. Nothing, no power will give me 0 or a negative number. So this does not exist. A logarithm cannot have an inside of 0 or anything negative because no power will be able to give me a 0 or a negative number as the actual result. To what power did I have to raise 4 to get a 2? So 4 to which power is equal to 2? Well, I have to take a square root of 4 in order to get a 2, and a square root is a power of 1/2. And then finally here, to which power did I have to raise 4 to get a quarter? So let's write this down too. 4 to which power is equal to a quarter? Well, we notice that 4 just got flipped to be on the bottom, and that corresponds to negative power, but 4 stayed 4, so the power here is -1. Logarithms have an incredible history of how they were actually discovered and where the word comes from. When they were originally discovered, they were not discovered as inverses of exponential functions, but rather as a really useful tool in navigation and approximations of small numbers. We will talk about how that's useful in log-log plots and semi-log plots and seeing the difference in trends. For example, I am sure you guys have been seeing log plots in the news about the pandemic, and that is the main application of logs for when they were first discovered. However, they also luckily turned out to be inverses of exponential functions, which allowed us to do much more efficient computations with them. The next slide is completely for you to actually practice with, but I will go through one line just to show you what the slide here is after. It is just getting a little bit more familiar, switching between an exponential form, a logarithmic form, and what they mean altogether, so that we are better prepared to solve equations that involve exponents and logarithms. So the first line here is completely filled out for you. 2 to the power 3 is 8. which means that logarithm base 2 of 8 is equal to 3. Sometimes it's easier to go the other way around, because this is the power to which you have to raise 2 to get 8. The other way to think about this is logarithm 2 base 8 is the power to which you had to raise 2 to get 8. So instead of writing a 3, we can write log base 2 of 8 there. Sometimes logarithms are not going to be nice whole numbers, so this notation will come in handy as well. So with the same type of logic, please go through and actually figure out the other lines. Once again, just so you get familiar with the notation. And then the next slide is just talking about comparison. Of course, you'll have calculators that can calculate the exact values of the powers and of logarithms. But again, just to build intuition and how this will help us in solving the equations, it's a really useful exercise to get familiar with the notation. I'm not going to go through the power ones, but let me just talk maybe a little bit about this logarithmic one. So it's asking which one is bigger, log base 9 of 80 or log base 9 of 82. Remember that logarithm is the power to which you have to raise the base to get the result. So this first logarithm is the power to which you had to raise 9 to get 80. And the second logarithm is the power to which you had to raise 9 to get 82. Now the powers here might be easier to compare than the actual log values. So all of these exercises you can do without a calculator. And I strongly encourage you to, in fact, do just that once again, so that you're more familiar with how the power functions work, the exponential functions work, and so that you're more familiar with the logarithmic notation, so we can use it later more efficiently in applications. Here's a famous quote by Michael Crichton from the Andromeda Strait, claiming that if we allow unbounded multiplication of a bacteria, that it will actually soon take over the earth. So he's saying bacteria multiply geometrically. 1 becomes 2, 2 becomes 4, 4 becomes 8, exponentially, and so on. So they follow the 2 to power something rule. In this way, it can be shown that in a single day, one cell of E. coli could produce a super colony equal to the size and weight of the earth. Let's actually check this claim. So we have that starting with a single cell, how long will it take for E. coli colony to reach the mass of the earth if we know that every bacteria doubles or splits into 2 every 20 minutes? Now, we know that the mass of one E. coli cell is 10 to the minus 12, and we know that the overall mass of planet Earth is 6 times 10 to the 24. So first of all, we have to determine how many cells will it take to reach the mass of the Earth. We know that this is the mass we have to reach, and we know that this is the mass of every single cell. So how many cells will have to go into the mass of the Earth? We have that the number of E. coli cells needed will be the mass of the Earth divided by the mass of each single cell. And remembering the exponential rules, we know that when we're dividing, we have to subtract powers. So overall result will be 10 to the power of 24 minus 12, which is 36, which means that we need 6 times 10 to the 36 cells. That's a lot of cells. Now, let's think about how they actually multiply or double. They double every 20 minutes. So what is going to happen in t minutes? How many doublings will have occurred in t minutes? So in t minutes, there are how many doublings that have happened? Let's think about numbers. So in 20 minutes, there's 1 doubling. In 40 minutes, every 20 minutes, every cell doubles. So in 40 minutes, 2 doublings have happened, the first 20 minutes and the second 20 minutes. In 60 minutes, there were 3 doublings, the first 20 minutes, the second and the third. So in t minutes, there are t divided by 20 doublings. That's how many times the bacteria have doubled. So what is the overall number of bacteria in t minutes? In t minutes, there are this many doublings, and therefore 2 to the power of t over 20 cells in total. Every time they double, So however many doublings they had, it's 2 to the power. And here we have our exponential function. Now, what we would like to know is, what is this value of t at which we will reach the mass of the Earth, which is this many cells? So all we actually need to know is, when are these two numbers equal? What value of t gives us equality between these two numbers? So I'm going to have 6 times 10 to the 36, and this should be equal to 2 to power t over 20. This is where cancellation laws will actually come into play. I have my variable, my t, in the power, and I'd like to bring it down. I would like to be able to actually calculate this. The operation that will allow my power to come down into the front is taking logarithms. Now notice that the base here is 2, so I can take logarithm of base 2, but I can also take logarithm of base e, or natural logarithm, anytime. I usually prefer to do that anyway, so we're going to take lns of both sides. Everybody has a calculator, so it's not that calculating ln of a specific number is going to be very difficult. So according to the logarithmic rules, this means that this number now comes down to the front. So I have that ln of 6 times 10 to the 36 is equal to t over 20 times ln of 2. And again, I'm after t. So t here comes out to be 20 times ln of 6 times 36 all over ln of 2. And if you plug it into your calculator, this will come out to be approximately 2441. This is time, so we have to see what units was our time measured in, and of course we had minutes here, so this is in minutes. Now it's hard to tell how long that actually is, so we're probably going to get a better grasp of it if we transfer that into hours. So I can divide, there's 60 minutes in an hour, I can divide by 60, and it comes out to be approximately 41 hours. Okay, so Michael Crichton was a little wrong. It's not going to take a day, but it's going to take only just under 2 days for uninhibited, unbounded growth, if that's allowed, for the E. coli colony to really reach the size of the Earth. Now notice, of course, that this kind of unbounded growth is really not realistic, because the only way the bacteria grows or doubles every 20 minutes is if it has unlimited supply of food or sugar or whatever it is, and if there are no other restricting factors such as space or competition or anything like that. So generally, there are density-dependent models that will produce better modeling of population growth, but if it is unbounded, this is how fast it's going to happen. Let's take a look at logarithmic laws now. They have the corresponding exponential laws for each logarithmic law, but exponential ones are probably more familiar, whereas logarithmic will require a little bit more practice to really get comfortable with. Once again, let me draw your attention to the fact that this is really precalculus material. So if you're struggling with this, please take a look at the precalculus review package, the corresponding section of it. Cancellation laws come in extremely handy when solving equations involving exponentials and logarithms. These laws simply state that the two functions are inverses of each other, which means that applying one after the other will cancel each other's actions, and we will get the x that was the argument in the middle. For the logarithmic rules, some of the most useful ones are the first two, which simply state that the first one is the logarithm of a product is a sum of logarithms. And the second one says that if you have a logarithm of x to power something, this power can come down to the front of the logarithm. Also notice that there's no law or rule that will allow you to simplify a sum of logarithm, a logarithm of a sum, or a logarithm of a difference. So if you encounter one of these are not easily breakable into anything. So you will have to do something else to simplify that first. All of these laws are stated using natural logarithm or logarithm base e, but they apply all the same to any other logarithm base.
Let's now see how we can use the logarithmic and exponential rules in order to solve various equations that involve exponential and logarithmic functions. Notice that because, once again, this is a review of what you should have covered in calculus. I'm only going to do a few examples as opposed to a comprehensive coverage of this topic as you might have done in pre-calculus course. So if this is going a little bit too fast, make sure to review the pre-calculus refresher materials. So let's start off with this equation. E to the power of 5x is equal to 7. So we notice that our variable x appears in the exponent, and we have to be able to somehow bring it down in order to find the x. Isolate the x is always the strategy that we use in solving equations. Here, we need to bring it down from the power before we can actually isolate it. So the way to do that, of course, is to apply a logarithmic function to both sides. Now, generally, you're free to use the logarithm base that you're going to apply, and it can correspond to the actual base of the function that you have. But you can, in fact, always apply the natural logarithm and then potentially sort of work out with the conversion. Okay, so we apply the logarithmic function to both sides. So I have the logarithm of e to 5x is equal to the logarithm of 7. And now I'm going to simplify what I can within the logarithm. Now, one of the laws, what we called cancellation law, something like that, says that if I have a logarithm and the exponential function inside, the power of the exponent will come down. Okay, so overall here, on the left-hand side, I will end up with simply 5x. And on the right-hand side, I have logarithm of 7. Now, logarithm of 7 is just a number. You can plug it into your calculator and figure out what the number is. I'm going to keep this expression calculator ready because I don't want to deal with the decimals at this point. Now, we're in good shape because 5x is brought down from the power. So in order for me to solve for x, I simply have to divide both sides by 5. And this is going to be my value for x. Once again, you can plug it into a calculator and figure out what the actual number is. The next equation is very similar to the first one, except for instead of power of e, we have a logarithm of 5x. And so because the logarithmic and exponential functions are inverses of each other, I'm actually going to do the exact opposite thing of what I've done in part A, and that is raise both sides to the power of e. So here I'm going to have e to the power of ln 5x equals e to power of 7. And once again, remembering the laws, I noticed that if the exponential function and logarithmic function are applied back to back, then what I have back, because they're inverses of each other, is just the actual argument of the inside. So 5x. And on the right-hand side, I have e to the 7th. Much like ln of 7, e to the 7th is also just a number that you can compute on your calculator. And so here, once again, dividing by 5 on the both right and left-hand side, I get e to the 7th over 5, which is going to be some kind of constant. So these two seem pretty straightforward, but it's a nice, easy illustration of the fact that if we have exponential function, we're going to apply the logarithmic function in order to solve for the exponent. And if we have a logarithmic function, we're going to apply the exponential in order to get the variable from inside the logarithmic function. This one is a little bit more challenging because here we have two logarithmic functions, both with our variable on the inside. The first thing to note is to remember that logarithmic functions aren't defined everywhere, and we have to really think about the domain. So here, the domain of the logarithmic function will dictate that x is going to be bigger than 0. So the inside of this logarithm has to be bigger than 0, and the inside of this logarithm also has to be bigger than 0, which means that x minus 5 has to be bigger than 0. In fairness, I should have really done something similar to this here, where I should have pointed out that 5x has to be bigger than 0 in order for us to produce a admissible solution. Now, next step, I basically want to reduce this problem to the problem that looks like the problem in part B. I would like to combine these logarithms together so that then I can apply the exponential function to both. And the way to do so is, if you remember from the previous slide, let me pull it up so I can point out, it is actually this logarithmic law applied from right to left. What I have is a sum of logarithms, and the way to combine them together is they will produce the logarithm of a product. So here, if I start with the sum of the two logarithms, by the logarithmic laws, what I have is a logarithm of their product. and is equal to 1 on the right-hand side. And at this point, the problem looks like a more complicated version of this one, right? It's ln of something, and so my solution is going to be very similar. Okay, I'm going to raise both sides to the power of e. So I have e to the ln of x minus 5 equals e to power 1. And then remember that if e and ln are applied back to back, being inverse functions, they will simply give me the argument of the inside. So x minus 5 on the left-hand side is equal to e to power 1 on the right-hand side. Now, as I pointed out before, e to some power is just a constant, so this is simply a number, and I can open up the brackets on the left-hand side and move everything over to the left-hand side. So what I'm going to get is x squared minus 5x minus e to power 1, or just e, is equal to 0. Now, this is simply a quadratic equation, so all we have to do here is apply quadratic formula in order to figure out the solutions, and then make sure that we check those solutions against the domain that we are given by our original equation. I'm going to leave the rest of this for you to actually go through as an exercise, but let me point out a couple of very important things about this slide. So if we have a simple equation, e to power something equals to a constant, we can apply a logarithmic function to bring the power down. If we start with the logarithm of something, we can apply the exponential function to get the variable from inside the logarithm. And every other problem with exponential and logarithmic functions will reduce to one of these types. So if you are given something that involves 2 or more logarithms, you'll try to reduce it to only have 1 logarithm so that you can then go through the same strategies in part B here. Now, we've talked about the algebraic treatment of logarithms and exponential functions. Let's take a quick look at the graphs of the natural logarithm and e to power x, remembering once again that they are in fact inverses of each other. So for e to power x, we've already seen various graphs of 2 to power x, 3 to power x, and so on. E is simply a number that is approximately equal to 2.71828 and so on and so on. It's transcendental, which means that it never actually has a pattern, it never ends, but it is a number that you can generally think about as being somewhere between 2 and 3. So much like before, if we want to construct this graph from scratch, we can simply plug in numbers. So for example, e to power 0, anything to power 0 is always equal to 1. So we know that it's going to have this point as its y-intercept. E to power 1 is approximately 2.7. So at 1, we're going to have a point up here. And so on and so forth. If you plug various numbers in, you will see that we still get the general shape of the exponential function. Now, if I wanted to now sketch myself a ln of x, the natural logarithm of x, I'm going to go through similar thinking. So for example, ln of 1. Which power do I have to raise e to get 1? Well, this should provide a hint. Which power do I raise e to get a 1? That power is 0. So ln of 1 is 0. So I get this point right here. You can plug in a few other numbers to get the sense for it, but you can also remember the fact that graphs of inverse functions are actually reflections of each other in the line y equals x. So if I draw the diagonal y equals x here, the graph of a logarithm will be a reflection of the graph of e of x. So now imagine that you've drawn this in wet ink and then folded your page along this line. Where would the trace appear is actually going to be your logarithmic function, and it's going to be something like this right here. Okay, it's a rough sketch here, but this is the general shape of the logarithm of x. Okay, and you can use similar logic to produce the graph of e of x and its inverse. I'm going to leave this up for you as an exercise. All I'm going to do here is actually point out a few different limits that we can compute that involve both of these functions. So for example, we can think of what does e to the x approach as x approaches infinity, and what does e to the x approach as x approaches negative infinity. Similarly for logarithms, let's think about the limit as x approaches infinity of the logarithm of x, and as x approaches negative infinity of the logarithm of x. I mean, we can certainly get these values from the graph that we have just drawn, or we can think about them algebraically. So algebraically, if I plug in a very large number into the power of e, I'm raising e, which is again a number between 2 and 3, into a bigger and bigger and bigger power. So of course my number is going to get higher and higher and higher, producing infinity. If I raise it to the power of negative infinity, this is kind of like having minus x, or 1 over e to the x, which means that I'm dividing 1 by a larger and larger and larger number. We can also see this trait here, where plugging in smaller and smaller, bigger and bigger negative numbers ends up with the y-coordinate of this graph getting smaller and smaller and smaller, approaching 0, but never quite crossing the line, right? Because we can never actually get negative powers as the outcome. And similarly for the logarithmic function, we can once again read those off of the graph, but you will see that as x approaches infinity, the logarithm will approach infinity, albeit slower than the exponential. And as x approaches negative infinity, well, we don't actually have that here. So this limit is not well defined at all. Which limit can we calculate instead of that? Notice that the function here, the domain is x is bigger than 0. So the best I can do is approach 0, and not just approach 0. The best I can do is approach 0 from the right-hand side, right? I have to stay positive in terms of x's, but I can approach as close as I can to 0 from the positive side. The limit of the logarithm in this case is going to be minus infinity, as I can see that my values are getting more and more negative into the negative infinity. I encourage you to fill in this graph on your own, again, keeping in mind the fact that once you can sketch e to the minus x, producing the inverse of it is going to be simply reflecting in the diagonal.
Logarithms were actually invented to deal with very small or very big numbers. And so here we will establish what is that purpose, or what is that usefulness in the logarithmic scale. So first, just a little exercise. How long ago do you think a million seconds was versus a billion seconds? It turns out that humans are really quite awful at comparing very large or very small numbers. So take a second here and try to figure out how long ago was million seconds and how long ago was billion seconds. You will be quite surprised at the answer. Pull out your calculator and do some calculations. I'll come back to answer this in a little bit. This gets to the root of the problem. If we're comparing numbers that are all very small or very big, or we're comparing numbers that range from very small to very large, the actual scale becomes a little bit overwhelming. So for example, here we're asked to compare the size of a red blood cell, an ant, a human, a whale, Earth, and Sun. So something very small to something very large. Here are the numbers on the regular scale. So a red blood cell is 10 to the minus 6, right? Very, very small when this length is in meters. Earth and Sun are much, much larger quantities. So see, the problem is if I were to write a comparison between a red blood cell and a sun, of course, if I actually wrote out these numbers as numbers, one would be very small, one would be very large. A logarithmic scale allows to move these numbers down, compress them into something a little more comprehensive and a little more comparable. So the way we would do this is, you can think of that as literally just drawing another line here, except for now, here we will not have numbers as they are given, but rather have a logarithm. And in this case, it's convenient to take base 10 because that's how the numbers were given to us in the first place. So logarithm of base 10 of the length that was given. Different lengths are different here. So like the length of a human is the height, whereas for the red blood cell, it's the diameter. Okay, the way that logarithms work, remember that the logarithm is the power to which you had to raise something to get the length. If it's base 10 here, it means that the logarithmic scale will give us numbers to which you had to raise 10 to get the length. So as opposed to having 10 to minus 6, 10 to minus 4, and so on, we will just have the powers themselves. So here we will have -6, -4, -2, and so on. In that way, when we have quantities, we don't have to have numbers of really large magnitude and of really small magnitude. We will only be dealing with numbers between -6 and 10, something much more manageable and much clearer, depicting what are the actual trends. So the red blood cell would be right here, somewhere between -6 and -5. The ant will be close to -2, a human will be close to 0, and so on. So all of these will move right as they were, except for not 10 to some power, but rather just the power itself. Okay? For a little exercise, try to mark these numbers on the logarithmic scale. In order to do that, you'll first have to write them as 10 to some power. So this is 10 to some power, each one of them. And then on the logarithmic scale, you will simply actually write down that power. Coming back to this question here, once again, I encourage you to actually pull out a calculator and figure it out for yourself. 1,000,000 seconds is about 11 days. And 1,000,000,000 seconds doesn't seem like that much more, does it, right? But 1,000,000,000 seconds is 31 years. I told you humans are pretty bad at comparing large numbers. Logarithmic scale allows us to get a little bit of a handle on our inability to really perceive and compare large quantities. Once we have a logarithmic scale, a really useful application of that is semi-log and log-log plots. If you guys have taken biology or chemistry, you would have probably already seen them, or if you've been watching the news lately, of course, logarithmic data has been presented in terms of the number of COVID-19 cases confirmed in various countries. So let's see how that works and why that works. So here I'm asked to sketch y equals 5e to the x on a regular axis and semi-log axis. Okay, for the regular ones, we already know how to do that, but I'm going to delay sketching it until I have my second graph ready. For the semi-log plot, in fact, you don't need to know that it's going to be log-log or semi-log. We're just going to take logarithm of each side of the equation and then see what happens. So this is my equation, y equals 5e to the x. I'm going to apply a logarithmic function to each side. Whoops. And then I'm going to try to simplify this or apply logarithmic rules to it. So on the left-hand side, there's nothing to simplify. I just have ln of y. But on the right-hand side, I have a product. And from the logarithmic rules, I know that the ln of a product is the sum of ln. So it's ln of 5 plus ln of e to the x. And I can see that I can simplify this a little bit further because now here I have the power of the whole of the inside, and I can bring this power down. Notice, and this is essential, that I couldn't apply this rule here. I couldn't have just taken this power and have brought it down because this power was not the power of all of the inside. This 5 did not have an x on it. So here I'm going to have ln y equals ln 5 plus x times ln e. And ln e, of course, is just 1 because that's the power to which you have to raise e to get e. So I have ln of y is equal to ln of 5 plus x. So notice that it's kind of fortunate because we don't have ln, we don't have x under the operation of logarithm, we just have x by itself. That's why it's a semi-log plot. X happened to be just by itself, whereas y actually has logarithm applied to it. So only one of the variables is affected by the logarithm. Now this logarithm of 5, this ln of 5, is actually just a number. You can plug it into a calculator and get an approximation for it. So it's approximately 1.61, and then I have a plus x. Okay, now just so I don't drag this ln of y around while I'm sketching, I can rename this into capital Y, keeping in mind that that means ln of little y, and I have 1.61 plus x. Looking at this expression here, if I were now to sketch it on little x, big Y axis, what kind of shape would that be? I have y equals some number plus x, so this is just a line. And this is key. By simply applying logarithms to both sides, I've managed to transform an exponential function into a linear function. So sketching both of them on a set of corresponding axes, here's what we're going to have. So my first graph is going to be just little x versus little y, and my second graph is going to be little x versus capital Y, which is ln of little y, right? So this is my capital Y. So the first graph here is 5e to power x. If I try to calculate the y-intercept of it, I plug in x equals 0. I'm going to get a 5. That's too high. Let's say it's down here. And I'm going to have a standard exponential shape like this one. For this graph here, it's just a line. The slope is the coefficient in front of x, which is 1. And this is my y-intercept. It's 1.61, or remembering where that came from, that's ln of 5. So my x-intercept here is ln of 5, and the slope of my line is 1. So I can mark it with that. And this is my line, ln of y equals 1.61 plus x. So once again, simply by applying logarithm to both sides of my equation, I've managed to transform an exponential looking graph to a linear looking one. This is if you start with an exponential function to begin with. Let's see what happens if you start with a power function. So where x is in the base and the number is in the power. And we're going to do the exact same thing here as we did last time. I'm going to apply logarithms to both sides and then try to simplify as far as possible. So for the first step, I have something very similar. The left-hand side here, nothing to simplify again. And the right-hand side, first of all, it's a product. Once again, this power is only on x, so I can't bring it down quite yet. So it's ln of 5 plus ln of x cubed. And now that this cube is covering all of the inside, I can bring it down in front of the logarithm. So ln of 5 plus 3 times ln of x. And this is exactly where difference is going to be. Remember last time, because it was ln of e to power x, once x came down, I only had ln of e left, which was 1. Here, ln of x is going to stay as is. And this is what makes for a log plot, not semi-log, because both my x and my y are affected by the logarithmic function. Okay, so once again here, I can rewrite ln of 5 as its decimal expansion, which is approximately 1.61 plus 3 ln of x. And now I can also sketch it on the set of different axes, except for here, again, both x's and y's get transformed. So let me call this y capital Y, and this ln of x capital X. And now I see something very similar to what I've seen last time. This again is just a line, but it's on the set of axes that are actually ln of x and ln of y. Okay, so this is once again a line. Let's now try to sketch both of these on the standard axis and then on the log axis. I'm sketching them for mostly just positive values of x because these plots are extremely useful in applications and more or less are only used in applications where x stands for the number of something. For example, the number of confirmed COVID-19 cases. So that means that it will be a positive number and I only need to look for positive values. So if I sketch just x versus y, then I'm sketching the function y equals 5x cubed. 5 will simply stretch out my function, and 5x cubed otherwise looks like a familiar snaky curve. Whereas if I sketch it on the log plot, so this is capital X or ln little x, and this is capital Y or ln little y, what I can see here is that this is just a line. This is the y-intercept, and again, remember that came from just being ln 5, so my y-intercept here is ln 5, and the slope is 3. So this power on the function became the slope of my line. Okay, so my line is going to look something like this, and it's going to have slope of 3. So what this allowed me to do is, by applying logarithms to both sides, I've managed to reduce my function to a linear function when both of the axes were logarithmatized. Okay? Try to do the same thing. I'm not going to go through this. It's very similar, but try to do the same thing with 5 over x, which is just 5x to the power minus 1, to see how the negative power will affect the outcome. Exponential functions look linear on semi-log plots, and power functions look linear on log-log plots. The reason we would like something to be linear, and you'll see an application in class, is because lines are really easy to find equations of. So if you give me, all you need here is to give me 2 points, and I'll be able to construct an equation of the entire line. Our ability to come up with equations of lines easier is exactly what makes it worthwhile. Now, in terms of where do we see these graphs, again, you probably would have seen them in your biology or chemistry classes, or we see them all the time in the news now. So these are COVID-19 plots from Ontario. BC graphs are not terribly useful to look at because we flattened the curve so early that both of the curves of regular numbered cases and on a logarithmic scale look kind of similar. So let's look at the graphs here. This is a graph of the physical number of cases that occurred. So 5,000, 10,000, these are the actual number of confirmed infected cases. The second graph is a log base 2 of the exact same thing. So these numbers are going to be log base 2 of the above. So this is a semi-log plot, whereas this one is log base 2 of your y value here. Why is that useful? Remember again that semi-log plots, exponentials look linear on semi-log plots. That means that if I look at the log plot and I see linear tendencies, that means that the actual disease spread is exponential. Here, it's very hard to see anything when the number of cases is small, but on the log graph, we can already see really high sloped linear tendencies here. So this allows us to see trends linear on a semi-log plots, which means exponential in real numbers, much earlier. The thing with small numbers here, right, because this is a big scale between 0 and 5,000. So when we say, let's say 100 cases versus 200 cases, the difference there was not very clearly seen on the graph. Whereas here, the difference between 100 cases and 5 and 200 cases would have been way more emphasized. Okay, and we can see the exact same picture in other provinces that have had a much bigger outbreak than BC. So for example, in Alberta, if you look at the regular graph, it looks like everything was going fine until just about, mid-April. Whereas on the logarithmic graph, you can see this exponential tendency much earlier. You can already see a huge linear increase here, which once again, of course, corresponds to an exponential increase in cases on the actual total number of cases. And so if you look at logarithmic graphs, you're able to act much earlier than if all you're looking at are graphs of the actual total numbers.
As we just saw with COVID data, sometimes looking at raw data is not very helpful because it does not reveal relationships within the data. And that is when we are going to take a look at the logarithmic data of the two dependent variables. So here's another application that talks about wingbird wing beat frequency that decreases as bird mass increases. And we have ourselves some observational data from the 3 different species of hummingbirds in terms of their body mass and their wing beat frequency. And we can see that that relationship seems to hold. The bigger the bird, the less often it actually beats its wings. So we can try to plot the data as is and find the actual relationship between the points, but the exponential relationships are hard to find from raw data. So instead, what we're going to do is we're going to assume allometric dependency, allometric meaning power or exponential. So we have body mass M, and wing beat frequency f, and they are connected by this exponential relationship with the a and b as some sorts of constants. And our mission here in this particular application is to actually find the values for the a and the b. So what we're going to do is we're going to start with the relationship that we're given. So f is equal to b m to power a, and we're going to take logarithms of both sides so that we can take a look at whether it's a semi-log or a log-log plot. So remember that on the right-hand side, when I'm simplifying it here, this power a is not power of the whole thing, so I can't just bring it down to the front right away. First, I have myself a product, and I have to work that out as the first step here. So the logarithm of a product is a sum of logarithms, and once I have that, now I can bring my power a to the front and have logarithm of m as a separate thing here. So now I notice that if I am, as the question states, to consider a logarithm of one of my observational data values versus the other, I will have that logarithm of m can be my x, logarithm of f can be my y, and then the rest are really my constants. So here, if I am to rewrite this, let's take a look at what would happen if I were to rewrite this in terms of x and y now as stated. So I'll have y is equal to ln of b plus a times capital X, and interpreting this as its own graph in terms of capital X and capital Y, I can see that this is simply a line, and within this line, this a is the slope, and this ln b is the y-intercept, okay? Once I have realized that, I can actually sketch this line. So let me take this relationship over with me to the next slide. And what I'm also going to do on the next slide is actually transform these two columns. Because I am now going to be working with ln of f and ln of m, I don't need these raw numbers. I need to take logarithms of all of them, compute them, and actually work with those values as the points on my new capital X and capital Y graph, okay? So I'm going to take logarithm of everything that's in the table, and here is what I get. So these values are logarithms of the corresponding values before, and now this is my capital X, and this is my capital Y. So my capital X is going to be my new axis, capital Y is going to be my new vertical axis, but like really I should keep in mind that this is just ln of m, and this is just ln of f. Now the actual line, as I had defined on the previous slide, is this one, and it's good to remember that the relationship that I assumed from the beginning was that f is equal to b times m to power a. Now let's take a minute and actually plot these points on the graph. I would like to see where do they all lie, okay? Take a minute, if you have the actual question printed on paper, take a minute and actually plot these 2 points. Let's call them something. Let's say the giant hummingbird is going to correspond to the point labeled G, the volcano one is B, and the blue-manted thornbull is B. Take a second here, sketch your 3 points. Here are what my 3 points look like. Again, this is not an exact sketch or anything like that, but this is a good approximation where the points actually lie. And here we notice that they do look like they lie along a straight line, which actually confirms our reasonable assumption that this corresponds to an allometric relationship. So what we can do, of course, is actually try to draw the line through all of these 3. My line is going to not look great, I'm sure, but do our best to draw the line. There we go, not so bad. The iPad corrected my inability to draw straight lines on a glass surface. And there we go. It looks like the points approximately lie on the same line. And with lines, we know exactly how to find them. So what we're going to do is pick 2 points on this line. My iPad chose V and G to draw the line through, so I'm just going to pick those 2 and find the equation of the line through those 2 points. Now, if you chose two different points to draw the line from. Your data is just going to be a little bit different. So of course, any 2 points I can draw the line from. So if my line ended up looking like this, it's going to be G that doesn't quite match the data. But again, it's not too far off of it. So pick 2 points to draw the line from, the line through. Any 2 points will uniquely determine the line, and then we're going to find equation of that line. Now, if you're going to follow the video along, I'm going to pick again points V and G. They were sort of chosen for me. So I'm going to take a look at these coordinates and find the equation of the line through them. Please pause the video and actually find the equation of this line for yourself. Okay, so what I have is if I have taken these 2 points, I would end up with the equation of the line that has the slope minus 0.51 and the y-intercept 4.27. Now, it's actually easier if I label these once again. So this is my slope and this is my y-intercept. And the reason that this is easier is because I can now see that the slope, the slope corresponds to the value a of my original exponent, and the y-intercept corresponds to logarithm of b of my original factor multiple in front of the whole thing. So now I can isolate those separately and solve for a and the b. So I'm going to have that my a is straight up equal to the slope, so minus 0.51, and my b I don't have directly, but I have that ln of b is equal to 4.27. So solving this for b, I'm going to raise e to power both sides. I'm going to end up with e to power 4.27, or if I calculate this as a number, it's going to be 71.7. This is fantastic. I have the value for a, I have the value for b, which means that I have my original model fully solved for. So rewriting this in terms of my original model, I have that the relationship between the beat frequency of the bird's wings is value for b, so 71.7 times its mass, m, to the power of a, minus 0.51. This is an extremely powerful technique because let's think back about what we actually did. We assumed that the 2 variables we were interested in were connected by a power relationship or exponential relationship. We cannot easily model this. We cannot easily solve for 3 points to be on some kind of exponential curve. So we took logarithms of both sides of our equation, transformed our data, and instead of having to come up with an equation of an exponential function that they pass, all we had to do was construct a line, which we have a lot of practice doing already. We've then interpreted the constants corresponding to the line in terms of our original constants and got the equation of the model as we stated it. Isn't this great? We started with an exponential, turned it into a line, and we're able to solve the entire thing by simply coming up with the slope and the y-intercept. Exponential functions are well known for doing a very accurate job of actually describing population growth on a short-term basis. And this is something that we're going to take a look at in the next class, but here's a little bit of motivation if the model is already given. I strongly encourage you to pause the video here. These are the types of examples that you should have seen a lot in precalculus, so this should look very familiar to you. So I have here that the population of hares at Mill Lake from 1960 to 1990 is given to us by this formula, where the total is in number of hares and t is in years since 1960. The first question is, what was the initial population in 1960? Well, 1960 corresponds to time being 0, so all I'm doing here is computing the population numbers at time equals 0. If I plug in 0 for t here, I notice that my entire power is going to turn into 0. Anything to power 0 is just 1, so overall I have simply 68. And again, next time when we start developing these models in the next lecture, we're going to see that the number in the front of the exponential, if the function overall looks like this model, corresponds to the initial value of the population. So in 1960, there were 68 hares. The next question is, what was the population in 1980? It's important to keep the timeline in mind. So here t corresponded to 1960, which means 1980 is population in 20 years. T is equal to 20. All I am doing here is plugging in 20 for t, nothing very difficult just yet. Plugging this into calculator should yield approximately 173 hairs. Now, the numbers you're going to get are often not going to be integers, so round up to the nearest bunny. The next question is, when will the population triple? So when means I am looking to answer the question at what time, and triple, well, triple from the original, if I started with 68, triple means I have 68 times 3, whatever that number is. Okay, so my original model is given to me by this, and I want to know for what t is this number of bunnies going to equal to 68 times 3. So let's write that down. My number of bunnies in year t is given to me by my model, and what I want to know is when is it equal to 68.3, whatever that number is. Now, the reason I didn't actually multiply 3 in is because I can see that I can now divide both sides by 68 and actually get rid of it altogether. So my next line will be a simpler version of this equation that looks like this. And now this is also really handy because I have isolated e on one side, and you can see that this is the form of the equation from a few slides back when we were simply practicing with solving them algebraically. So I can take logarithm of both sides. I can bring the power down using that technique and then solve for t. So a few steps later here, if you're approximating, you should get that t is, I'm going to write out the calculator ready formula, 0.467, which approximately is 23.5 years. Now remember that our timeline started in 1960, so 23.5 years later will be around mid-1983. And that is going to be my answer here. The final part of the question is asking, what will the population size be long term? I already mentioned this and we will talk about it more next time, but the exponential models usually describe the growth best on a short-term periods. Even 30 years is probably too many. However, the question here is asking what is it long term? So what we're interested in is taking the limit as time goes off to infinity, again, more mathematically rather than practically, of the population size. So let's actually rewrite this limit with the population model. So 68 e to power 0.0467t, and think about what this limit approaches. As t grows larger and larger, I'm plugging in bigger and bigger numbers in for t, which means that my power keeps growing, and therefore e to this power approaches infinity, and therefore the entire limit itself approaches infinity. So we understand that this is basically why these types of model are not very good for long term, because no population will really approach infinity. Eventually they will come across various constraints such as size, space, and whatnot. Now here, because we have all of the information, we can actually sketch a quick graph of our function. We can see that the beginning is 68 hairs. So at time equals 0, we have ourselves 68 hairs here. And then we can, of course, even plot this number if we're going to try to come up with a reasonable function here. So for example, in 20 years, we know that it's approximately 173 hairs, something that looks like this. And I am going to fit an exponential looking function to these 2 points. Now, I know that it's not reasonable to have time before 0, but I'm going to sketch it just so that it sort of fits with my overall shape of the exponential function. But this is essentially the shape that we are looking for overall here. Okay, once again, we're going to be working with a lot more of these functions in the next topic. For the final example here, let's take a look at a logarithmic model that you likely have encountered in your other classes, and that is the pH. The pH is actually a common measure of the acidity of a solution, but it is defined as a logarithm, in fact, a negative logarithm of a concentration of hydrogen ions in the solution. Okay, so pH is itself a logarithmic measure. We know a couple of common values for it. In particular, the pH of pure water is 7, and solutions that are more acidic have lower pH. Solutions that are less acidic have higher pH, which is what this minus sort of does. We also know that acid rain sometimes has pH as low as 4. What the question here is asking is essentially to compare these two numbers. So in terms of the pH, which is the logarithm, we can compare 7 and 4, but what we really would like to know here is how much greater is the concentration of the hydrogen ions in acid rain than it is in pure water. Okay, looking at just these two numbers, you can sort of say like, oh, I don't know, maybe almost 2. But remembering that this is a logarithmic scale, we have to be careful. So let's once again think about what this actual logarithm does to the values themselves. In terms of acid rain, we have that the pH value is 4. So if I were to write this out, I will have that 4 is negative logarithm of the hydrogen concentration in acid rain. So in acid rain, if I am to solve this equation for the actual concentration, notice that I can essentially move minus to the other side and then raise both sides to the value of whatever base of the exponential function I want. I'm actually going to go with the easiest choice of 10 because this is logarithm base 10. So I'm going to raise both to power of 10, remembering that then these two functions are actually inverses of each other and will cancel out. So overall here I have that the concentration of hydrogen ions in acid rain is 10 to the negative 4. I can follow through the exact same calculations for pure water. So I have 7 is negative log of the concentration of the hydrogen ions in pure water, and solving for this will give me 10 to the negative 7. So if I'm comparing the actual pure concentrations, these are the two numbers that I have to compare. So here, how much greater? Well, we can divide one by the other, right? So combining these two together, I can take a look at what is the ratio between the concentrations in acid rain and the concentrations in pure water. And remembering that the exponentiation rules, when you divide, you're subtracting powers. So overall, I'm going to have 10 to the power negative 4 minus 7. So negative 4 plus 7. So 10 to the power of 3. 10 to the power of 3 is 1,000. That means that the concentration of hydrogen ions in acid rain is 1,000 times greater than in pure water, right? So when you're comparing the numbers of the actual pH, the actual numbers that correspond to the concentration itself, the raw concentration, are much higher. What the logarithm does is bring the numbers down to some kind of scale that we can understand better than dealing with very, very spread out values. The same type of logarithmic relationship also holds for things like decibels when we're comparing very small numbers, and for things like earthquake or Richter scale when we're comparing very large numbers. So we have to be very aware that the numbers we're seeing might not represent the actual factors of the relationship that lie below them.